Alright, this is new to me as well, but welcome to a talk virtually about JVM performance. I really hope this is recording, which makes a fine difference between giving a conference presentation and sitting alone in your basement talking to yourself. It's special times, and I hope, I guess we all know that it's probably the best that we don't travel as much as we used to. It's a shame that we can't meet in person and have this talk face to face, but we know what it's good for. If you got sick or if any got sick on this trip, I guess we would be regretting. So let's make the best out of it, as long as the situation is in place, and we'll just try next year, right? Alright, but doesn't stop us from discussing a topic I've been working with for a very long time, JVM performance. What I'm trying to do in this talk is to basically discuss how a Java virtual machine is working when it runs your code, and how it tries to make it faster than it would be without these optimizations. And what I'm trying to do is to basically show you how a Java programmer would optimize code, and not how I find many performance talks approach this, by showing you machine code and by talking about hardware and processor pipelines and so forth. I try to make an approachable presentation of this topic that is accessible to everybody, right? So, how does a Java virtual machine run code, or how is a Java program executed? And as you all know, like if you write a Java program, you will compile it using Java-C, and this will render the source code that you write to Java bytecode. And already Java bytecode is a bit of a cryptic format to many, but all in all, Java bytecode is very much a direct translation of a Java source program to a better machine processable language. It's already basically normalized in a way, and bytecode it doesn't have formatting issues. It's binary. It can be transformed over the internet very quickly, which was important at the beginning of Java, when applets and so forth were still the driving factor behind the platform. But the magic normally happens between the JVM and the processor. How is this bytecode actually executed? How is it rendered into machine code instructions? And if you want to understand Java performance, this is where you have to look at. You can't really look at Java-C, because Java-C is not applying optimizations, more or less. It is doing a very few basic cleanups, more I'd say, and optimizations, but it's not an optimizing compiler. So we try to go a bit deeper today and then show you where things happen and how they happen, and also of course how you might be able to debug performance bugs, because those happen obviously in the JVM, and I'll explain you also what a good approach is to writing performance programs there, right? So how does the JVM process bytecode? So any Java class represented as Java bytecode is in the first step of a Java program. It is interpreted. It's actually run instruction by instruction. So if you run a program that adds number A and B together and then returns number C, then the interpreter will just do what you tell in bytecode. It will load number A, it will load number B, it will apply an addition, and then push back value C. Right, and how this works is that the JVM includes machine code templates. So for certain bytecode instructions, it already knows how the best way to run those is, and then it will use these templates. And for every bytecode instruction, so every source code instruction in a way, it will execute this machine code template. Quickly after that, though, from the machine code templating, which is also called level 0, it will evolve, because the JVM is an adaptive platform. It's tiered, so it will start in interpreting. All programs will start being interpreted, but then the more a program is run, or the more a segment of your program is run, for example in a loop or a web server, like in any repeated manner, it will be promoted in a way to more important code. This is where the name comes from, Java HotSpot, right? It finds hotspots, important parts of your programs, and it will try to improve runtime from this mere recreation of how you wrote it in your source code, right? So C1, then the client compiler, how it is called in this tiered compilation process, has 3 stages, which are less about performance than they are about profiling. And this is what makes a JIT compiled language a JIT compiled language, or what the reason is that JIT compilation just in time, basically during the runtime of a program. So JIT compilation means that while your program is running, JVM will be analyzing how it is executed, how your program is actually executed, and then use this profile information to, in the end, hand your program over to the C2 server compiler to use this information about observing your program in action to make it as efficient as possible. And this is what the JVM is all about. It's a profile-based optimization approach. So you start just executing your code simply. You will then, for example, look, is this if statement ever true or is it ever false? Then this information of observing how your program is actually used will be used to apply a speculative optimization to run your program in the best manner, given the way you are currently running it, right? So, as said, everything starts out interpreted. You will then typically jump to level 3, so these levels don't have to be passed level by level. And in this level, you will collect all kinds of profiling data, and then given this data, in the end, HotSpot or the JVM will try to make the best out of it. An alternative path is, because of course resources are restrained on any machines, so if you are already profiling a lot of code, this profiling itself will cause overhead, and every profiling approach is a trade-off between running your program and optimizing your program, or using resources for that. So if the JVM is very busy, it will send code to, for example, level 2, where it just applies some simple profiling. Then when the machine gets a bit more less busy again, it will then promote it again to advanced profiling, and then in the end put it on C2 again. Another option, which is also typical, is that it starts profiling a method and then realizes, oh, you know what, this is too trivial. Think of a getter or a setter. I don't have to really do optimization on this method. So I don't have to really use resources on making it better right now. So this is basically what all the JVM is doing all the time. It will start running your code, it will analyze it, will look into how it is executed, and in the end try to make a most efficient program out of it. Right. So, and in order to look into what profiling information is collected and how the JVM then speculatively optimizes your code, the most important factor to understand is the building block of a call site. So the JVM, or at least HotSpot, is a method-based JIT. It's not a tracing JIT, like for example Android is a tracing JIT, so it's not trying to focus on the method level, but for the most, the JVM is a method level JIT, where a method as itself is compiled. So every Java method is a compilation unit that can be improved to be a better performing method. And a call site in this context is if you call a method from a method, like here within do something you call val bar, you will be able to perform optimizations that are the most crucial to how performant your Java code will be executing. So because if you run val bar on some class or some instance of a class, you don't really know what code you'll be executing. In this case, you can just say, alright, it will just be bar, but it is an indirection. So a program, or any program, stores the data of a method, so the executable of a method, somewhere in your memory. And whenever you jump from one memory location where the do something method is located, then you'll have to apply a redirection to travel from the do something method to the bar method to invoke it, right? And these method calls are virtual. Some languages, like in C++ or C#, you actually have to declare methods to be virtual to allow overriding them. And the reason for that is simple, is that it is expensive to travel through these indirections. It's not expensive in an absolute manner, but it's expensive in a contextual manner, because if all a program is assembled of are method calls, then jumping from one memory location to another all of the time will of course slow down your program, right? So how is this solved in Java? How are virtual calls possible in Java, which was actually quite unique for the language when it came out? So how can Java be still performant despite having all these indirections, all this jumping from A to B? So as I said, a virtual method call per se isn't really expensive if you think of it. If you go back, if you arrive at this val.bar call site, what you would have to do is to look up where the implementation of bar is located. For this purpose, the JVM entertains a so-called V-table, virtual method table, for every single class that exists. So for class foo, there will be a V-table where all methods from all subclasses are positioned, and it will then basically have the signature of the method and a location of the code to this method in order to execute it. So for foo, you have this method table, and like the 8th entry for the bar method will point to some location where the system.out.println hello world is located. However, if you overrode foo in a subclass and you override the bar method, so then this method shouldn't be executed anymore. Then of course the JVM will have another method table, which is a direct copy of the old one, to point to this other address, while the other methods that aren't overridden will just point to the addresses of the same methods as before. And the reason for this copying mechanism is that since we have single class inheritance in Java, the method pointer will be at the same index as for all superclasses. So whenever the JVM discovers a call site, like this one we've seen before, val bar, it will just, for example, jump to the sub v table, to the 8th location, the 8th offset of a signature method, and invoke the code that is pointed there. And that's not much, it's a triple indirection. First you discover a call site, you have to discover then the class that the instance is invoked on, do a null check in a way, which is handled a bit differently than that, but then you have to jump to the memory address and you have to run the code, right? So it's not expensive, but as said before, if you do this a lot, if this is essentially what your program is doing all the time, it will still be expensive. So how can we improve on that? And this is something that JVM doesn't do, but this is something Smalltalk did, for example, most famously. Smalltalk also had virtual methods for everything. You could override everything, and they also had performance problems based on that, because you had to jump around and you had to look up methods all the time. So how did they approach it? They just added caches, and we as developers all know that if you have a problem, just add caches here and there, and then typically it might get better, and until it doesn't, because caches overflow, and if you don't hit caches properly, you will have the same problem. But to some degree in Smalltalk, having local caches worked very well, because many times methods aren't overridden ever, right? So as long as methods aren't overridden, which is a assumption that holds for many call sites, then it doesn't work. And even if a method is overridden, as long as a particular call site is always invoked with a certain subclass of a type, then it will still work with the cache. So when you discover val bar and the cache already has the address populated for this type, then you can just jump there, and only if you miss the cache, then things will get more expensive, and then they will get even more expensive than with the V-table. But as said, heuristically speaking, and programming languages, dynamic programming languages work a lot with heuristics, you will be fine, very likely. So now you have a cached link, and we have a double indirection instead of a triple indirection, which is a speed up of 30% after all, which is pretty good for programming platform. But as said, the JVM doesn't do that. The JVM rather works with monomorphic, so-called linked call sites. So whenever the JVM discovers that you call a method on a variable or at a particular place in your code, call site, it will just go to the method directly. Instead of having a cache or a check, it will add an assertion to check if the type is correct, and as long as this is the case, it's always the same class, it will just jump there directly without conditions. And this doesn't seem like it's cheaper maybe to you as like a cache where you still check in and walk or do a miss, but the way how processes work, this can make a difference. So first of all, the assertion doesn't have to be applied immediately. So processors can reorder instructions and then undo work that was done in expectation that certain assumptions hold. So that if that happens, it's very expensive. But as long as the assertion holds for the most time, this is fine. This is actually how exploits like Spectre were built. It's around making the JVM execute, or not the JVM in particular, make a processor execute instructions that it is not supposed to execute, to just yield the result of it somewhere from cache lines, right? But all in all, on oversimplified speaking, we do these assertions and then we can just jump somewhere and then execute the code directly. Still, however, we have to travel to a different memory location. But the next trivial optimization based on us having added this assertion is that we can just inline code. But before we look into this, let's look into all the call side types we have discovered now. And if you just take this single thing out of this talk, the call side mechanism, you have already understood a lot about the inner workings of the JVM. So call sites in the JVM can be monomorphic, they can be bimorphic, and they can be megamorphic. And if you read performance blogs, you will discover these terms a lot. So a monomorphic call site in the JVM is a direct link to another code position. And heuristically speaking, so by just looking into how an average Java program is assembled, about 90% of all call sites are actually discovered to be monomorphic by the JVM by running profiles and by then speculatively saying, alright, I'll just assume this to be true for now and then build my optimizations on top of it. If a call site discovers at most two classes, like let's say you have an array list and a linked list at a list call site location, right? Then this call site will be bimorphic, and typically that's holding for data structures. Those will still have a direct link, but it will be just guarded by a conditional. So it will say if instance of array list, go to this location. If instance of linked list, go to this location. Else uncommon trap, just fail the whole thing, and we'll reconsider how to run this code now. Polymorphic means in a way megamorphic is also polymorphic. Bimorphic is of course also polymorphic. Everything that's not monomorphic is. But the JVM only knows a distinction between bimorphic and megamorphic. And megamorphic, if you have a tight loop that needs to run performant, then what you have to do, simple performance engineering on a JVM, is you have to avoid megamorphism for call sites. So make sure that call of a method on a variable always hits the same class. If you have more than two classes being discovered there, then you will end up doing a vtable lookup, meaning that you have 3 times the dispatching costs compared to the direct links, and you lose on a lot as well, which I will show you later. The famous exception is if you have a so-called dominant target. So let's say you call a method bar on variable foo 1,000 times, and if 90% of these calls are on a particular class, then this class will be dominant target and will still be treated as if it was monomorphic, and then all the other classes will still be vtable lookups, but at least the big fraction of hits on this call site will be performed, right? And the JVM is basically starting with a vtable lookup in the worst case. It will then use this profiling optimization, see what class was invoked the last 10,000 times this method was called. Was it always the same class? If it discovers that, it will just transform the call site to a monomorphic call site and recompile the method into machine code where the monomorphism is applied, adding this uncommon trap where if the call site suddenly isn't monomorphic anymore, the compilation unit, the compiled method, will just be thrown away and be recompiled again with a virtual method table lookup. So when you start your JVM, basically it starts out slow. It will collect all the data about how your program is working, and then the longer it runs, it will basically try to find a good balance between making your code efficient and making it flexible, because if your code needs flexibility by changing targets all of the time, then of course it is much cheaper to use vtables rather than using direct links where you always have to throw away your code. And if you have followed the development on JIT compilation and the JVM, then you will have heard about Graal maybe, which is also a JIT compiler, but it offers a way of also compile your code ahead of time. And as you might know, like I guess you can imagine that all this optimization, de-optimization at runtime is expensive in terms that it needs code, it needs resources to optimize the code as well as it does to run your code. And by ahead of time compiling some fractions of your code, which are fairly static, you can of course save you these costs. And of course also the startup, the first 20 seconds of your JVM process will run much faster, which is very attractive for short-lived processes, because JIT compilation in this context isn't really suited for programs that only run for 5 seconds, because once you have reached the optimization state, the VM will die and all the profiles will die with it, right? So if you are curious about ahead of time compilation, it has its place. It is very much a useful technique, but for business applications, I still think that JIT compilation is the way to go. And this is what, if your process runs many hours, then often looking into your profiles is making your code much more efficient. And especially if you write programs based on libraries where you probably will not use all the functionality of these libraries, the JIT-based profile collection will look into library code just as it will look into your code, and then remove all the library code more or less that you don't need for you, and just run the hot paths that you execute in the way you execute them. So this is just the general idea of how the JVM works and how the optimizations work. And if you want to make sure your program doesn't get slow, just make sure you don't have megamorphic call sites on your hot path. And why is that? And I'll show you in a second. So now that we've established call sites and monomorphism, megamorphism, if a method is monomorphic, so you can just jump into a location where some code is added, why not just copy the code where you have the GOTO statement? Best case, the GOTO instructions are all about as much code as the actual instruction. And for a getter or a setter, this will very much be the case, because then a getter and a setter, there's not much code to have. And now, not only have you saved yourself from the indirection, but you created a bigger chunk of code that an optimizing compiler can process again. Because as I told you, JVM is a method unit compiling JIT. So it takes a method, and by inlining code you just made the method bigger that is the target of the optimization. So typically, and this is why my monomorphism is so important, or at least biomorphism or a dominant megamorphism, is because you can now apply all the other techniques that the JIT knows, right? So, and once you lose the monomorphism, all this is gone, right? So this is why it's often called so-called uber-dominant optimization, and this is why it's so important to keep getters small and setters small, because if they were complicated and megamorphic and overridden many times, right, then you would lose the ability to inline setters, and then calls to data wouldn't be field access anymore, as they typically end up being, but they would be expensive virtual method dispatches. And then if you have like a JSON processing step where you read all the data from many data objects, then this will get much more expensive than it should be, right? Yes, and in this context, it's good to know, because this is a pattern I see a lot as well, that every type matters. So let's say you have a list and you don't know what type the list is. It might be an array linked list. Then list.size will be a bimorphic call, right? As we just learned, it can either be an array list size or a linked list size, which have both different implementations. But now people want to be brief with their code, so they use this technique called double brace initialization, where they they create a constructor of a subclass of ArrayList, if you've seen this ever. Because the first brace opens an anonymous subclass, and the second brace initializes a constructor. Initialize a block which is added as a constructor. So, but now you have created a new type. Now you have ArrayList, linked list, and this anonymous subclass, meaning that if this anonymous subclass hits the size method, you will have turned the call site to be megamorphic, which it wasn't before, right? So look out for these sort of things. If you can have a nice deterministic code path, the JVM will be thankful, because in the end, determinism, predictability, is what makes programs fast, and not only because the JVM knows how to do speculative optimizations and be less often false about its assumptions, but also because how computers work in general, with prefetching of memory and so forth. The more prediction you can give, the better, right? And ironically, you could micro-optimize this, right? If you had an interface with 3 implementations, this would by definition be megamorphic, right? Because the magic number of 3, less 1 is observed to be dominant. So what we could do is we could instead have 3 static methods, sub1, sub2, sub3, and have a field that now represents what instance of a subclass from before we'll be considering for an instance. Now we just switch on foo, the ID, and invoke the corresponding static method. And now, since we don't have one call site like we had here with the m method, we now have 3 call sites, which each are, by definition, static methods are always monomorphic. Monomorphic. Now we have micro-optimized the program. And if you do certain types of applications on the JVM and you want to force the JVM in a certain state, then this can be very helpful, because then now you control the narrative, right? You trick the JIT compiler into doing what you want exactly, and you don't leave it to chance or small fragile changes in your program. But generally this is not something you want to do, but it's something you can do, and it's nice to experiment and to compare the effects of things, right? Alright, mentioning inlining as before, and why inlining is so important. I mean, now we're half an hour in the talk and I'm still talking about inlining and monomorphism, but this is the big thing. This is what most people look into when they analyze programs for their performance. Let's say you have this method, a log method, and normally you don't use println, right? But that's just for the sake of the example. Assume we log to println and we have this log method, and you might recognize this log method from the signature somewhat. It's not that different to how many logging frameworks look like. So now you call this log method, right? Now we have arguments and we iterate over these arguments, and they're of type object, and we call toString on all of them. Now, after all we've learned so far, this call site toString method will most likely be megamorphic, because any type can be in there, right? So let's look at an example. We log foo, the number 4, and new object. We have 3 types, a string, an integer, and an object, and we already crossed the magic barrier. So now logging will be really expensive and really slow, which is of course something we wouldn't want to do. But thanks to the log method being static, we know that the log method at least is monomorphic, meaning that the log code will just be inlined. And now we have something to chew on, or the JIT compiler has something to chew on. And the first thing it might do is to unroll the loop, as it's called. So it will see, alright, there's a loop on 3 arguments. Instead of allocating an iterator, I'll just take the 3 arguments and basically duplicate the system out println in there 3 times. And now, thanks to the unrolling, we'll have 3 call sites instead of 1. And this is where things fall into place, right? Because now these 3 copied call sites have suddenly become monomorphic. So what the JVM can now do is it can just basically eliminate the boxing, of course. The foo toString is a no-op because it's toString on a string is just as the value itself. So we'll discover all these things as well. But thanks to inlining, all the following optimizations have become possible to begin with. So it's only thanks to that JVM is faster. Even if the indirection of megamorphism isn't so expensive by itself, the consequences are often rather drastic, because you lose all the potential of optimizing a method by not being able to inline its dependent method calls, right? And all programs are typed. This is not only a Java thing, this is a compiler thing generally. So even if you look into JavaScript, for example, the same techniques are applied, only that it is less obvious. So if you look into V8, the runtime between Node.js, and you have this object through JavaScript doesn't have types, doesn't have classes. It has types, but it doesn't have subtyping of any object type, right? But V8 does, of course, because V8 has a compiler and wants to make a Node program quick. So whenever you define a class or variable that is an object in Node or in V8, the V8 will add a hidden class for it. The star indicates here an object without any properties. Once you add a variable to the object, it will create a subclass, more or less, that is now having the value x. And once you add another one, you will have the type xy, being a subclass of x, being a subclass of star. The next person comes along and defines the very same object. We already have seen this one, but now we define y first, meaning that now you have a subclass that is different from x, and as a consequence xy, or yx rather, yx and xy, even though being the same object from a programming perspective, will not be marked to be equally by V8. And the simple reason for that is that keeping track of that those two classes are the same most likely is more expensive than the benefits of it. So it's a trade-off, and to be honest, I haven't looked up how V8 has developed in the last 2 or 3 years, so this might as well have changed, but it was like that for a long time, and most likely it's still like that because it's a pretty fundamental thing. So even dynamic languages that don't have any type systems, typically in their compilation phases add as much information as they can, or their interpretation phases add as much of this type information as they can, because deep down the processor just treats bits being bits and then shifts them around, right? So you kind of have to tell the processor and the operating system what these bits mean, of course, and the more information you have about the data you're processing in advance, and that's what's the crucial part is, the better, because processors are very fast today, but you have to prefetch data, and if you don't know what data to prefetch, and that data I not only mean the actual data, the input to your program, but the program itself, the better you are aware of what path of your program you will be walking down, the more of this program that you want to execute you can basically put into the caches of the processor to being loaded when it's time for it, right? And then basically that's all I try to explain here. The type information of a typed programming language like Java is very useful, not only to you to assure quality and correctness of your code, but also to compilers, to optimizing compilers, and that's the same as it's for Java, as it's for Python, as it's for JavaScript. All JITs want to know what the things they process actually mean, right? And in JavaScript, it's not always easy. Yes. Alright, so now we've covered a lot already for an introductory talk about performance. So I'm basically closing now the method call side chapter, which is the major chapter, and then just quickly look into other performance measures in compiled programs, like branch prediction, which is the other big topic, but it's less interesting because you have less control of it. But let's say you have 20,000 random values between 0 and 100 generated by this pseudo program here, and then you iterate over them 1,000 times, and if a value is bigger than 50 you add it, and if it's less than 50 you subtract the value, and then you will end up with some sum. how can you make this program faster? So turns out in Java, so first of all, this is a conditional. A branch is a control flow, and branch prediction basically means, can you predict, are you gonna end up in the if or in the else? So you can make this program faster by adding array sort, and that's not very intuitive, as you, I guess. Yeah, of course it's not, because why would it be faster to do more than to do less? And the reason simply is that modern processes do work speculatively. They will try to execute code before it is actually known which path of a branch you'll be taking. And the reason for this is what I mentioned before, is about data pipelines for CPUs, where they preload a lot of data to actually keep the processor busy, because processors are stalling a lot, meaning they're not doing anything. And if they, for example, knew in this case, they sort an array that most likely the next 10,000 values will be positive on average, then it can just start adding 10,000 values without even checking the branch. And then only if it finds out that the branch was mispredicted, that we didn't end up in the if statement half of the time, then it can still unroll or roll back instructions that it has already applied, and that is cheaper than not knowing whether to add or subtract a value, because the values are actually randomly positive or negative. So by sorting, you add predictability to your program, helping the CPU to just do a lot of work very quickly and then just correct a few mistakes it makes once you've reached a barrier where a positive value crosses over to being a negative value. Right, so this is again the same idea basically from megamorphism and monomorphism. The more predictability you add to your program, the faster it will execute. Right. Yes. It's of course too simple, but in all this is how it works. It's a good enough example for educational purposes, so that's why I'm using it. Alright, I only have 3 more minutes, so in-person talks go quicker apparently than virtual ones, but a last one to look into, which is interesting now, is escape analysis. So we all write this code, and many of you might know that this is just synthetic sugar for writing this code. And this code, of course, has an object allocation. It allocates an iterator, and allocation isn't as expensive, but garbage collection is actually fairly expensive compared to many other operations. So you probably might want to avoid this in a program that is very short and needs to be efficient. So why not use the old syntax for iterating over a collection, the for index notation. So it turns out that the JVM can look into this code and find out that this iterator is only needed in a certain scope, and then since this instance will never escape, it can just delete it. And by deleting it, it never gets allocated, so you will have all the benefits of writing your code efficiently, or how you want to do it in an object-oriented language, that you delegate responsibility to objects without paying the costs. And unfortunately, HotSpot has been rather bad at escape analysis. So if an instance escapes a method, then typically it will be allocated in a heap. But it has gotten better, and Microsoft, I think, has started to contribute a bunch of things in this direction to make escape analysis better. Alright, and it's been 40 minutes. I have a lot more material, but I've given this talk a bunch of times, and I try to cover different areas every time. So if you want to learn more, you might just Google this title of the talk and find more information. So I'll just make a very quick jump to the end, and you'll see how much we've skipped. But it's kind of my trademark to not get done with my slides, so I'll just stick to that. But thank you so much for virtually attending my talk. I wish we could have met in person, but it is how it is. If you wanna meet me virtually, and it's a good thing, maybe I saved a bunch of time on traveling, so I have more time on following up my open source work and my community outreach. So just get hold of me on Twitter, Rafael Codes, find me there, find me on my webpage. Find my open source project, mainly ByteBuddy, which is something I work with, a code generation, and just reach out if you're interested in these things. Thank you so much. Have a good rest of the day or night whenever this will be streamed. Thank you. I'll see if the recording actually recorded now, and I'll be very disappointed if it hasn't. But see you around, and stay safe as long as this disease is around. We don't want to spread this more than we already did, so let's hope to keep it contained. Cheers. Bye bye.